Okay, I guess we're at time. So good afternoon, everyone. Thank you for coming to our Birds of a Feather session on Vulkan. My name is Ralph Potter. I'm Samsung's principal representative within Kronos. And since September of this year, I've had the honor of being the Vulkan Working Group chair. So we have a packed agenda today. I'll start us off by talking about Vulkan's latest update to the core API with Vulkan 1.4, which we launched on Tuesday. After that, other colleagues from the working group will share some details about other topics. So Spencer from LunarG will talk about the Vulkan software development kit. Spencer does heroic work keeping the Vulkan validation layers up to date and has a great overview of the state of the ecosystem and the many. Are we not on? Okay, let's try that again. I hope you heard half of what I said, but let's go back to the Spencer bit. So Spencer will talk about the Vulkan software development kit. Spencer does heroic work on keeping the Vulkan validation layers up to date and has a great overview of the state of the ecosystem and the many tools and software components that we all rely on. That will be followed by Cai Kangying from Huawei discussing HDR support in Vulkan, and by Zhang from AMD talking about GPU-driven rendering and the AMD shadering queue extension. And then the last two talks of the day will come from Shannon from NVIDIA. So NVIDIA's research compiler, Slang, has recently been brought under multi-company governance within Kronos. Shannon chairs the newly formed working group that oversees that work. And for our final presentation, Shannon will also follow up with a talk on Vulkan Safety Critical. And then at the end of the session, we'll close out with a few minutes time for questions. So if there's anything you were curious about during the presentations, we'll be happy to address that there. So first of all, a bit of an announcement for anyone who wasn't present at our Fast Forward event earlier in the week. On Tuesday, Kronos announced Vulkan 1.4, which is the latest revision of our core API. I'll spend the next 15 minutes talking about Vulkan, what Vulkan 1.4 provides, our process for developing Vulkan, and what to expect for the future. So, in case anyone's not aware, Vulkan is a modern low-level graphics API. It's focused on delivering high performance, explicit user control, and predictable low CPU overhead. Vulkan's undergone a bit of a transition in terms of how we organize and plan our work in the last few years. So hardware roadmaps are many years long. And if the working group and our users want to evolve the API in a particular direction, and that direction requires hardware changes, then we need to give hardware vendors sufficient notice of that change of direction. So as a consequence of the changes that we made around Vulkan 1.3, we're now in a position to be able to plan far enough in advance to be able to do that. So this is a bi-directional process. As a low-level API, Vulkan has always reflected the properties of the hardware that it runs on, and that's not going to change. But now we'll be able to discuss how we want the API to evolve and discuss whether changes can be made to future hardware to accommodate that. In that sense, the future needs of the API can now be one of the many inputs that contribute to future hardware designs. And a final point here, our work in Vulkan is driven by our users and the needs that they communicate to us. Along with the hardware vendors, we also have the major engine companies such as Epic and Unity, the platform vendors such as Google and Valve, and other important software vendors actively participating in the working group. Beyond that, we have a much wider set of developers on our advisory panel, and Vulkan is the result of that collaboration between our end users and the hardware vendors. One last point here, I'll note that every single comment that gets posted on the Vulkan spec GitHub repo gets read and discussed by the working group in our maintenance pools. So if you have a use case that's not being addressed, please do let us know, and that's the place to do it. So, some of you may have seen a version of this slide before. Vulkan is everywhere. It runs on hardware from all the major GPU vendors, and all the major game engines support the API. It spans a wide range of hardware from embedded devices like set-top boxes through mobile handsets and portable gaming devices, all the way up to powerful desktop and server class GPUs. In the early days, we described AAA game development as our primary customer. That's still a really important market, but Vulkan has grown beyond that. We're seeing good adoption in professional graphics applications, like the offerings from Adobe and Autodesk. API translation layers like Angle and D3D Proton and Zinc have become really important consumers of the API and bring massive amounts of content to the API. No other modern graphics API has the breadth of platform and hardware coverage that Vulkan does. Vulkan is also the only open standard modern GPU API. It's available across Windows, Linux, and Android. It's on embedded systems and some console platforms. All of the major GPU vendors are involved, along with the most significant platforms and engines. And Khronos' multi-company governance model ensures that the API is open to all of us to use and extend to meet our individual market needs. Anyone can come to Khronos and get involved in the development and the evolution of the API. So before I get onto the details of what's actually contained in Vulkan 1.4, I'd like to talk about the purpose of core API updates like Vulkan 1.4 versus the roadmap milestones that we've been releasing. The process of how we evolve the API today and what you might expect going forwards. So we first released Vulkan 1.0 in 2016, and we've released revisions of the core API roughly every 2 years since then. We view broad adoption as a goal for the core API. It's not just about tomorrow's highest specification GPU with the latest features. It needs to be supportable across a wide range of offerings that our IHV members produce. With Vulkan 1.1 and particularly 1.2, we had features that we wanted to include in the API that couldn't be supported everywhere. And we resolved that by making them optional. In retrospect, that didn't provide the greatest developer experience. Having optional features in core isn't meaningfully different from having a bunch of individual extensions the vendors might optionally choose to support. So with Vulkan 1.3, we decided that new functionality in the core should be mandatory wherever possible. This made the value of the core API version clearer, but it also highlighted that the set of features we were delivering in core was quite small. Now, in parallel with the development of the core API, we've been working towards standardizing more features with a roadmap for nearly 4 years now. So where the core API is focused on support for current GPUs, the purpose of the roadmap was to be more forward-looking and allow us to reach an agreement on what common set of functionality new and future devices should have. So with Vulkan 1.4, we decided to start taking advantage of that and have been able to deliver a much larger set of mandatory features as a result. So the roadmap is an ongoing process that we started about 4 years ago now, and we're increasingly starting to see the benefits of this advanced planning. Internally, we have a sequence of milestones describing either a set of functionality or a set of problems we want to solve for things that are further out. For more challenging problems, this roadmap stretches out as far as 2030. Each milestone is a line in the sand for implementers, setting the pace of development. We publicly shared the first milestone in 2022 and our second in 2024. By planning in advance, we're able to get agreement on bigger features like dynamic rendering and push descriptors, standardizing these for new hardware in 2024. You can expect to see future milestones published on a 2-year cadence, with the next scheduled for 2026. Now, with core versions, we're aiming to answer a simple question: what can we do with current hardware in the market today? With Vulkan 1.4, we were able to use the 2024 milestone as the starting point for our development, giving us a huge head start. Driver implementations are typically shared across product lines, and so hardware vendors have already had implementations of the features contained in the 2024 milestone, or they had an understanding of which of their hardware offerings couldn't support individual features. They also had plenty of visibility into which functionality contained in the roadmap milestones was likely to make its way into the core API. So this gave us plenty of time to prepare. The consequence of all of this is that we were able to bring you Vulkan 1.4 earlier than we originally planned. It was supposed to be next year, but we're early. And we were also able to bring a more compelling and complete feature set than we might have ended up with if we hadn't had all of this process. So, on to what's actually in 1.4. Over the next few slides, I'll touch on a few highlights of what Vulkan 1.4 brings. But before I do, I wanted to just give a brief overview. So we've promoted 16 extensions, including dynamic rendering local read, host image copy, shader float controls 2, and push descriptors. We've incorporated the maintenance extensions up to maintenance 6, which address a collection of small niggles and minor issues that we found over the years. And we've gone back and we've made a whole slew of features that used to be optional, mandatory, and made a number of minimum hardware limits more stringent than they used to be. So when we designed Vulkan 1.0, we needed to pick a minimum feature set for devices that would be able to support Vulkan. We chose to match the requirements of OpenGL 3.1. That corresponded to mobile handsets that were available in the marketplace at the time we started Vulkan 1.0. I should point out that OpenGL 3.1 launched over a decade ago in 2014. Until Vulkan 1.4, we hadn't really revisited those minimum requirements. During that time, hardware has evolved. In some cases, previously optional functionality has become ubiquitous. More importantly, in some cases, it had become almost ubiquitous, but a single vendor or a single hardware part remained an outlier. Vulkan 1.4 takes many features that were optional in previous versions and makes them mandatory. At the same time, it raises many minimum values on hardware limits. Over time, this should reduce fragmentation and complexity for application developers as Vulkan 1.4 becomes more pervasive in individual markets. So I'd like to use scalar block layout as an example here. The original extension for this was released in 2018. It's been optional in core since Vulkan 1.2. Being able to rely on having C-like layouts in your uniform buffers is really convenient. Having to code around the possibility that it might not be there is really irritating. It's unnecessary effort in most cases. The extension is widely supported, but it's not on 100% of devices. And so developers had to make a choice as to whether to do that extra work or to drop a class of hardware. Making it mandatory in the core API helps us eventually move to a place where it does become ubiquitous and where developers don't have to worry about that last 2% of devices anymore. That will take some time, but putting it in core helps us get to that place. So now I'm going to pick on a few highlights from 1.4. Most Vulkan applications are going to want to copy images to or from host memory at some point. The most obvious use case here is loading texture assets from disk. Depending on the application, the ability to do this without interrupting rendering can be really important. Think of something like a large open world game where you're going to want to stream in terrain textures as you explore the world. For a good experience, you don't want rendering to start stuttering as new assets are streamed in. In unextended Vulkan, copying textures to the GPU involves populating a CPU-accessible staging buffer and then issuing a command on the GPU timeline that will perform the copy, along with potentially transforming the memory layout of the image into something more optimal for the access patterns of the GPU. The GPU work involved in that copy was not guaranteed not to interrupt it or delay rendering. The ext host image copy extension enables these copies to be performed by the CPU. This avoids stalling rendering and potentially provides additional benefits by avoiding the need for a staging buffer. Some GPUs have dedicated DMA engines to handle this streaming already, and these can be used where available to avoid consuming host resources. So Vulkan 1.4 implementations are guaranteed to provide at least one of these two methods of streaming large amounts of data to your device. Okay, so the next one I wanted to talk about, so Vulkan 1.3 promoted the dynamic rendering API into core. That API greatly simplified rendering code, removing the need for render paths and frame buffer objects. It's been extremely well received by the community. but that API didn't address subpasses and input attachments, and these are critical for performance for tile-based GPUs. Tile-based GPUs are the dominant GPU architecture on mobile, and so it was important to address that gap. The dynamic rendering local read extension addresses that and brings dynamic rendering to parity with the older render pass APIs. It allows the use of pipeline barriers within dynamic rendering, as long as those barriers have the by-region bit set. Support for local reads from color attachments and storage resources is mandatory. Depth stencil and multi-sample attachments are optional, but I'd anticipate that they'll be widely supported. As someone who works for a mobile vendor and who wants developers to have a great experience bringing Vulkan content to mobile, I'm personally really pleased to see this one. Nice. Okay. Vulkan is more than just a specification. Our ecosystem is made up of a lot of components, and they take time to update and release. So the specification and header files have been available since Tuesday. The desktop loader is also available in source code form, so you should be able to build that now and have the tools you need to start development. The merge request to open the Vulkan validation layers is up and expected to land in the next few days. Spencer tells me hours. He told me days yesterday. Okay, great. The pre-built SDK will be available in January. It contains a large number of components maintained by teams across many different companies, and the process of getting all of that updated to the latest API version and fully tested takes a little time, especially during the holiday season. Finally, on implementations, all of the hardware vendors, all of the desktop hardware vendors, and the majority of mobile vendors successfully passed our conformance process already. NVIDIA have desktop drivers available today. Mesa has Linux drivers available for a wide range of hardware, and I'd expect that drivers will be available from the other desktop vendors soon. Mobile and console markets have their own platform-specific processes, so talk to your platform vendors if you're interested there. Now, as I get to the end of the presentation, just a brief promotional announcement. For the past 2 years, we've been running an annual 3-day conference dedicated to Vulkan. We ran the first one in Munich and the second in San Jose in 2024. They were both excellent events with around 100 to 150 attendees. Vulkanize 2025 will be next February, hosted by ARM in the HQ at Cambridge in the UK. Videos of content from the last events is available on the Vulkan YouTube for you to check out. Registration is open now, so please consider whether you might like to attend. I'll just leave this slide with a few useful links up for a moment. In particular, you can find a link to the actual spec here. That points to the new documentation site that we launched this year, which is much more friendly than loading the old monolithic spec. The documentation site pulls together many Vulkan resources that we produce. The spec itself, the Vulkan guide that Spencer put hours and hours into, the Vulkan samples, Vulkan tutorial. It's great to finally have a single unified searchable resource there. There's also a link to the GitHub repo, which is where you should go to post feedback or to report any issues with the spec. And finally, a link to the community Discord where you can talk to many other Vulkan users and get questions answered by the community itself. Finally, a thank you from myself and all of the working group for listening. We hope Vulkan 1.4 brings real improvements to all of our developers, and we'd love to hear your feedback and get your input on where the API needs to go next to meet your needs. Please feel welcome to come and talk to us or to post your feedback on the Vulkan Docs GitHub. Our next talk will be from Spencer with an update on the Vulkan SDK.
Oh, I just want to say it's so cool seeing so many people want to hear about Vulkan. You guys are all packed in here. So yes, my name is Spencer Fricke. I work at LunarG, and today I'll be giving you an update about what's going on in the Vulkan SDK. ラッキーなことに日本語を勉強したい、そして日本語でフォローしたい方はぜひ写真撮ってください。But yes, about me, I work at LunarG, been there for a while. I work primarily in the validation layers. I've been part of the working group, and recently I've been trying to do everything. My daily job is basically to make the Vulkan and SPIR-V ecosystem as good as possible. So speaking of the ecosystem, there's a lot. It's a big ecosystem, and the kind of question, there's only so many engineering hours, and so how do we decide what to prioritize? And the answer is kind of cheesy, but it's all of you guys. And by that, for one example, LunarG every year puts together a survey, and we get feedback. We've been doing this for a while. We get very valuable feedback from people. I just want to thank anybody who's ever spent the time filling out one of these surveys. We do read them all. Everything. Karen, my boss, puts a lot of time into this, and I just wanted to make an announcement that this February, keep watch of the Chronos or LunarG newsletters, social media, and you'll get notified about the next 2025 survey we'll be putting out. So the Vulkan SDK is a large software development kit. It slowly grows all the time. All the tools on the right are all the tools. They're all open source. You can go grab them yourself. What the Vulkan SDK really provides is we build these all for you. We make sure the versions are good. We do it on Windows on ARM, Linux, Mac. We make it very convenient. And about every 2 months, we package it up, put it on our website so people can grab it and get going with Vulkan. So noticeable updates from this last year. Slang, in the last SDK, we added Slang as a compiler. So now, doesn't matter what shading language you want to use, we have a compiler for you to test with. The crash diagnostic layer, I'll talk a bit about more soon, was added. Also, recently with a lot of new, there's been a new set of devices running ARM on Windows 11 devices running on ARM. We want to make sure people using those devices can properly get going with Vulkan. So we have an SDK build for that. And then some other noticeable things I don't have the time to dive deeper in. So this January, and we're going to say January because depending on the holidays and how fast it takes to get the 1.4 headers in, we'll have an SDK up, and that will be a 1.4 SDK, so you guys can get going right away. I'll also be talking about our new Vulkan Configurator 3 tool we'll be adding. And for people who are on Windows, in the past, when we installed the SDK, we didn't install the loader, but now that's going to just be automatic. So if you didn't notice, awesome. But if you did, it'll be fixed now. We always like to put these numbers out just so people are aware of the growth of Vulkan over time. So we show how many downloads we have on our SDK. I will preference always that the Linux one is probably way higher. That's only our tarballs, and we don't get any of the Ubuntu or Fedora package management numbers. So I'm assuming, but still, it's good to get an idea of roughly the trend. As you can see, obviously Mac has been growing, and then the ARM one is still kind of in too early to see, but it's definitely not zero anymore. So there's a lot to the SDK. I'm only gonna have so much time to cover some of the parts. If I don't cover a certain tool you care about, definitely find me after. So GFX Reconstruct, if you guys aren't aware, this is a tool that we have many engineers working on at LunarG. It's a 2-part tool. So it's it's a layer that will trace your Vulkan app. So it'll take all your Vulkan calls, all the memory, generate probably a multi-gigabyte large file, but then you'll be able to just point the executable to replay it. And so the replayer will then take the executable and just play it back. It kind of looks like a little video. And what this does is it provides a deterministic replay of your application, which is incredibly important for like hardware vendors or even us as like tooling who want to have both a deterministic performance regression, bug testing, way to test stuff. So, and then recently people have been wanting things such as, making it work across different GPUs and platforms. It gets very messy, very fast. So a lot of stuff in that space has been being worked on. So validation layers, this is where I spend most of my time. Our big thing for 2024 was improving error messages. We know that sometimes you get an error message and it doesn't really help because you just know something's wrong. Doesn't tell you. We spent a lot of time, and there's like 20,000 VUs, so it took a while to really try to give you a better, information about what happened and why you got the error. And I will tell people this. I strongly will suggest that if you ever do get a validation layer error message and it doesn't fully make sense, that's a bug in my opinion, and you should please open an issue on GitHub. I check that page 4 times a day. So if you make an issue, I will see it. And we want to make sure error messages are good. Also, we just want to make sure we don't have any false positives. We want people to think of us kind of like, your compiler. You hope your compiler just works. We want you to hope that the validation layers just work. And that's kind of been our goal for last year. So inside the validation layers, we have, when you call a function call, there's actually many, we call them internal, I don't know what we call them anymore, but we have the core validation. That's like your generic default, checks everything. But then we have these optional features that you can turn on: best practice, GPU AV, and sync val. So GPU AV is this was added in about, I want to say 6 years ago, and it kind of just sat stale as we didn't have dedicated time to put on it. This last year, with the rise of GPU centric extensions, shader and queue, work graphs, ray tracing, device generated commands, we wanted to really focus on providing people with GPU side tooling, because there's just certain things you can't validate on a CPU. The classic example is if you have an array of descriptors and you have a variable that's indexing into it, we don't know until you execute the shader if you've been out of bounds or not. So we do things like instrumenting your shader, prevent you from crashing, reporting the error. So this has been a lot of focus in the last year around this. So if I haven't got to your issue, it's probably because I've been busy on this, so I do apologize. So next is sync val. The number one thing we got in the survey last year was to add timeline semaphore support to sync val, and we did. So Artem, who's our wizard who works on this stuff, he added it in the last SDK. He's currently adding lots of error message support, and in the future we want to make it so GPU AV can detect if you read or read a variable. Well, sync val doesn't have that capability at the moment, so we're hoping to this year to merge that together so sync val get more fine-grained knowledge. Also, Artem's our dedicated artist in LunarG, and he likes generating art. You didn't get the joke, the sync is a sync val. Working on Vulkan all day can be daunting. We like to keep it fun around here. So Vulkan configurator, if you haven't used it, you're missing out. So there's lots of layers in Vulkan. The ordering matters. They all have settings. It can be awful to do that all from a command line terminal. So we created this tool many years ago as a UI, a graphical user interface, to control those layers. And then we created a second version because naturally we found all the issues. Well, we found more issues, and we just wanted to redo it completely one more time. So Christoph has been working tirelessly on this, and we're hoping unless something happens, it will be ready to go in the January SDK. He likes these animated graphics. So for example, this one, you can quickly make a new layer. For someone like me who needs to constantly test multiple versions of layers, this is a fantastic addition to easily be able to bounce between. He has the bottom, you can kind of see it. It shows you which order they are in. So because the ordering does matter in a layer, because you got one's going to take the function call before the other. And then we don't see it on the top. If you click on those, the preference and the help, and all, there's probably new ones now he's been adding, provides us a lot of nice information about the whole layers. So trying to make layers useful and more enjoyable to work with. So Crash Diagnostic Layer is a new tool. We've taken inspiration from the Stadia team who had a tool similar. And the whole design is to prevent you from crash. When you crash, it's annoying to figure out where it happened. And so this tool instruments your command buffers, does some other tracking. And so if you do crash, it'll have a dump file. It will zoom into the part that actually crashed as close as possible. And it's been very useful to help people who've been hitting, because once you hit a device crash, you'll do anything to get information and to try to figure it out. It is in early development. You can imagine testing this involves trying to purposely crash and hang your device. So it can be hard to test. So we are constantly looking for people with feedback. If you just post on the GitHub issue, email me, whatever you want, we will be happy to take your feedback. Jeremy Gibbon, who works on this, gave an entire talk at the American SIGGRAPH in June about this. So if you want more detail, there's an entire detailed presentation on it. So Vulkan profiles, this is something I feel like most people aren't aware, and it's pretty cool. So how I like to explain profiles is it's just a JSON schema. So Vulkan has an amazing, for better or worse, ability to support everything. Ray tracing, video, you name it, you can run it in a GPU. We'll probably support it in Vulkan one day. What this ends up being is hundreds of extensions, hundreds of limits and queries and properties, and it can be very hard just to know if your GPU supports everything. So you can now list all those things, like all the limits, the formats, everything you care about in a JSON file. And with that, we kind of open a new level of possibilities. So of course, like the roadmap Ralph just talked about, that's all described in a JSON profile format. Android has their own formats that they enforce. So anybody who makes, like for example, if you're making an Android GPU, you need ASTC texture support. That's in the profile. You must support that. And then what's really cool is people aren't realizing is if you're a developer and you have like 1,000 lines to query everything, you can just represent that all in a JSON file. And we have a library for you that will just return true or false so that you can really, that's what Unreal did with they've created a profile. And then with one function, they can quickly know if the device they're running supports that level of functionality that they care about or not. So there's a lot more to profiles. There's tooling around it. There's the JSON file. There's people are using it for different ways. I know if you have questions, I bet Rolf would love to talk to you about profiles. We've put a lot of work into it in the last few years, the working group, and it's been the basis for a lot of things. So we really think this is our way to solve just the sheer number of functionality you can have in Vulkan. So I'm doing. One more thing I want to throw out there is so if anybody doesn't know, Compiler Explorer is a fantastic tool made by a man named Matt Godbolt. It was designed originally to do like C++ code and see what the assembly is for. Well, someone poked at me and asked me to add shading language support to it. So recently I added GLSL and SPIR-V support. So now you can quickly go on the web, pop in your little shader code and run it, make sure it compiles, see what it looks like. All the beauty of that tool you can now get with their GPU shading tools. And as of breaking news, as of Friday, I added a PR to add Slang support, and as about 12 hours ago, it's actually live. So if you go to Compiler Explorer right now, you can GLSL, HLSL, Slang, SPIR-V, you can test it all now online. I'm going to continue adding more support to this. But this all happened because about a month ago, someone poked at me and said they would like that. And that kind of like wraps up my talk, which is saying, we need your help. Your feedback's important. I don't know what to solve unless you tell me there's a problem. So if you have questions, if you have any criticism, my last train's at midnight, I think. I will stand out there until midnight and like listen to your feedback, because we generally appreciate all your feedback. If it feels like it's getting ignored, it's not. It's just a lot. We can only focus on so much. If enough people complain about something, things get fixed faster. All engineering works. So just want to thank you guys all for coming. And then again, if you have any feedback, advice, things that you find just not fun about developing Vulkan, because it's already hard enough. We don't want to make it somewhat fun. So let me know after. And that's all I have. So thank you very much.
Right, so next up we have Cai Kangying from Huawei to talk about HDR support in Vulkan.
First, a short self-introduction. My name is Cai Kangying. So I came from Huawei 2012 lab. I'm leading a team focusing on graphic standard technology. Yes. Okay, so I'm glad to be here talk about later about the HDR support in Vulkan. Yes. So first, background. Why we care about HDR? The HDR thing is more and more popular in the industry for the moment. Starting from several years ago. As listed in the right, there are a list of games already natively support HDR. And for the video, so on the market, there are a lot of HDR video content. For example, I will give a number. For example, on the China market, there are 50,000 hours of HDR vivid content. HDR vivid is a standard by UWA. Yes. Then for the device, right now most of the high-end mobiles can take HDR videos. HDR photos and also videos. And for the high-end laptops, TVs, mobile phones, they usually have a display with over 1,000 nit, which is very good for display HDR content. Yes. Okay. So that's the background. Here then we would like to show you the difference between SDR output and HDR output. On the left image, it's an SDR output. Maybe you already noticed that in the sky, in the sky part, it's too bright and white, so it's overexposed. And on the right image, the sky part is light blue and with more details, which is much closer to the ground truth, to the visual quality we want to present to the users. Yes, I guess we don't have a HDR projector here. So I promise if you come to us to see the image on the real HDR display, it will look even better. So yeah, here okay. I hope you can notice the difference. Okay. Okay, then just how the two images are generated. They use the same input, same model, the same environment map. The most difference is the in the display part, how to handle the color space and the transfer function. Yeah, then why Vulkan? Why we implement the whole HDR pipeline use Vulkan? Of course, like Vulkan is a cross-platform API, not only for rendering but also for presenting. So based on by use Vulkan, the application is able to correctly display a HDR content across different OS, different GPU, and different display. That's the biggest benefit. Yes. Then I give you some introduction on how to display HDR content in Vulkan. We divided it into 5 steps. Basically, like the first 2 steps is set up the environment, get prepared. Then the third step is the render the content. Then for the fourth and fifth step is for display. I will talk them more in the later. Okay, so first step. We need to correctly set the surface format to a HDR format. So yes, the most of the surface format is in VK surface format, which including wiki format and wiki color space. Wiki format is the RGB10A2 things, and wiki color space include actually color space and the transfer function. Color space like BT2020 transfer function, which for example HRG and PQ. Here, so the wiki surface format already including a lot of HDR surface format, but we cannot choose the one we want. First we need to get the HDR surface format supported by your device using VK get physical device surface format. Okay. And for the next step, we need to get a presentable HDR image, which means like we need to create a swap chain and send the HDR surface format to the swap chain to get prepared for the later rendering. Then acquire a presentable image, which is normal, the same with the other process. Yeah. Okay. Then the step 3 is just rendering. Here, it's a simple example to render a reflective sphere and using an HDR environment map. Nothing quite new here. I won't go to details. So then we come to the step 4, which here is pretty important. We need to, in order to correctly display the HDR content, here need to manage the color space and transfer function carefully. As in previous step 2, we already set up the target HDR image, the target swap chain. Swap chains, color space, and transfer function. So in this step, we need to make sure that the HDR content we want to display, its color space and transfer function is consistent with the swap chain. If they're not consistent, some conversions need to be done. Otherwise, there are some flaws will be introduced. Some typical flaw is color shift. Yeah, here the example is like in the content might be sRGB, but the color space of the swap chain is BT2020. So we need to do this kind of conversion to make sure the content is correctly presented. Okay, then we can come to the last step. The last step, so the content is prepared. Generally, the content is prepared. So it's easy. We just we just fill the present info and call the VKQ present to present things. But things are not so easy here. So there's some application scenario is that the content only create once, but the created content need to be displayed on different devices. Then, for example, here we show an example. The content is created on display with 1,000 nits. The end device could wear from 500 nits to 2,000 nits. So for the 500 nits display, it's even don't have the capability to display the 1,000 nits contents, correctly display the 1,000 nits contents. So the final visual result really depends on the display system, how the display system handle this kind of situation. So some display system they will do automatically do the tomating, but that don't always work. Some flaws will be introduced here. Some unexpected contrast loss might happen here. Some display system they will just clamp the value to the range it can display. Then very often we will notice the overexposure, unexpected overexposure. So both those effects is not. We don't want it. We want to improve that. Here, so the one solution is that an HDR metadata can be sent together with the content to the display. The HDR metadata consists of some necessary information of the content and some parameters of the creator's display. then the display, it's possible like to achieve consistent visual effects across different displays. For example, like some HDR standards like HDR Vivid, HDR 10 Plus, and Dolby Vision can provide this kind of metadata. Yeah, to give consistency is very important, especially for some applications. They don't want to get a lot of complaint about why my phone shows different, like the quality is different on my phone with my friends. Okay, yeah. So that's some here we some other HDR display related extensions, including HDR texture compression. So the ASTC already support HDR texture compression, and yeah, so yes, Vulkan for the visual consistency things, Vulkan is also working on it. Working on it to provide some solution to that. So there's a new extension called Wiki Huawei HDR Vivid, is added to the Wiki HDR to the HDR metadata, trying to resolve the final display things. Yes, that's the reference. I think that's all my. Thank you.
Right. So Ken next to talk about GPU-driven rendering in Vulkan.
So hello everybody. I'm Ken. I'm from AMD. I'm part of the Vulkan core dev team, and my topic today is GPU-driven rendering in Vulkan because it has been a hot topic here in the Vulkan community. So I'd like to share the opinion from AMD. Just before I start, the standpoint that I want to make here represent AMD. So get to the next slide. So basically, first slide is about the motivation. So why do we want to achieve GPU-driven rendering? Because over the years, we have seen a lot of new extensions that come up into Vulkan APIs that really showcase what modern GPU is capable of. But there's one thing that really, I should say, remain unchanged, is that it still requires the CPU to kind of instruct the GPU about what to do. So usually you will have a situation kind of like a producer-consumer model, where the producer is the compute one, will do some pre-processing, sorting, etc. And how GPU work is supposed to be performed depend on the result, right? So, but in between, it still requires some intervention from the CPU saying that, hey, this is the result, go execute something, subsequently. So it leads to system bandwidth consumptions, increased latency. So we wanted to reduce this type of round trip to the host. Okay, and another dream of the programmer is that ideally GPU should be able to launch work by itself. So the translation is, first, GPU should be able to understand the dependency of GPU works and automate state changes, and finally avoid unnecessary GPU works through GPU culling automatically on the fly. And another angle is about GPU programmability, because right now it's not very handy that Vulkan API still function as local representation. So ideally, there should be a feature or extension that can depict the whole scene and send it to the GPU, so that the GPU can be kind of autonomous. So just a couple of weeks ago, Vulkan has a new extension called device generated commands. So I think this is a good answer to GPU-driven rendering, and I will introduce this extension specifically. So the name of this extension is self-explanatory. It just says it is a device rather than the host that generates the command. Okay. So, but before I introduce this one, I need to introduce some background. So, because for those who are familiar with Vulkan API, this extension is basically just an upgrade from indirect commands. So, get back to the first slide. So, instead of just fitting those parameters when you record the command, right? You can first put your those commands into the GPU buffer, and then during command recording stage, you'll say, hey, these are where those parameters reside in the GPU, go execute them. So in this way, the round trip to the host can be reduced, right? So it will lead to less bandwidth, right? So you can see it just turned out to have multiple job parameters in the GPU buffer. We call it indirect command buffer, and it will have API called multi-jaw indirect, right? And this extension basically pushes further by allow the user to specify or assemble indirect commands layout. So to give you two examples, the first one, you want to say, oh, okay, I want to have vertex binding, index binding, followed by a draw parameters. Or for dispatch, you say we have two data for shader as shader input, right? And finally launch a dispatch. Note that the final command must be one type of actions. I mean, draw, dispatch, mask, or ray tracing. You cannot bind all those objects without doing anything at the end. This is kind of the limitation of this extension. So it adds flexibility to customize the commands layout. So in this way, there will be no more VK command bind something in your command recording phase, right? Because they have been generated by the device. And another distinguishing feature is pre-processing, where you can overlap command generation with execution. You bundle a bunch of pre-processing steps all together, and it can be faster. In terms of memory control, so they will have a new object called pre-process buffer, where it is required by the driver and for the purpose of this extension, and it is opaque and it should be used for other purposes by the application. And as I said, in terms of expressiveness, from now on, all the shader input can be handled in indirect fashion, right? And another thing that deserve highlighting is that not only those inputs, but also shaders and pipelines can be bound in indirect fashion. So you can see you can put an index of shader or pipeline at the very first indirect command. So this is kind of very impressive. So what I use slash here is that if you use this extension together with ext shader object, then you basically can switch shaders. Otherwise, you can only switch pipeline, because shader is just pipeline without states. So here's the overall procedure. So first, if you want to switch shader or pipeline, you should need to create a bundle of them. So just basically a collection. So the prerequisite is that it should have the same input type. So that one input to one shader applies to all of them. It is for a compatibility reason. And then you determine a command layout, just same layout as the previous slide. Just shader switching, pipeline switching, followed by two shader input, and finally a draw call. So here you can have these four rectangles all together. We call it a sequence, and you will have multiple sequences that reside that is located in the GPU buffer. And then you do some necessary memory allocation, and then finally during command recording stage, you just call pre-process followed by the final execution. So the life will be a lot easier for the command recording. So in this way, the system bandwidth can be lowered. Well, it turned out to be a very powerful and useful extension, but it still has some downsides, I should say, intrinsically. So let's get back to the producer-consumer model, where you have a single producer that will generate some data for several consumers. Okay, and at this point, because we don't know like what is the result would be, so in case all those data go to only one consumers, we need to have to prepare the worst case sized buffer. And I can only draw 4 consumers here, but the reality is you can have maybe like 100. Then you can see how many wasted memory that can be possible. Then step forward, when we are at the command buffer recording stage, first of all, you need a barrier here, right? Because only those consumer can be executed after the producer is done with data generation. So it can be costly, especially if the execution time of the producer is not very uniform. So in this case, those data goes to consumer 1 and 3, and you can see the gray areas are all wasted memory. And also you will have wasted launch here because those ideal consumers are also in the command buffer, and it goes to the hardware, go to the command processor, and command processor figured out, oh, these are just wasted launches with the job pod this. And it can be an overhead as well. So like I said, there will be wasted launches, wasted memory. Another thing I want to point out is this extension can be somehow very implementation dependent. I mean, not only from the performance perspective, but also from the memory perspective, because an intuitively way to implement this extension on the driver is to, the driver can basically launch an internal compute shader to just read those indirect command buffers, fit out the real command, and send it to the GPU, right? This is why we have a pre-process step. You just launch the internal compute shader as a middleman. Or, like I said, you can directly tell the hardware what these indirect commands look like, and the hardware can directly consume those indirect command buffers directly. So it can lead to very different performance characteristics. And if you use compute shader if the driver uses compute shader implementation, then preprocessed buffer will be used to store intermediate results. And it will be proportional to how many sequence you will have at most, right? So, so the dream would be like, what if there's a way to express very complex dependency of GPU works, even embed some advanced algorithm. And also we want to avoid those worst case size buffer, right? And optimization and self-scheduling are also our concern, because right now the main role of CPU is just command recording. So if the GPU can launch appropriate work at appropriate time, then those CPU cycles can be saved and they will have lower bandwidth. So this is another extension. As AMD, we firmly believe that this is the extension that represents the future. This is called shader in queue. The X here means that it is experimental right now. And this is also known as work graph. And let's dive into this. So first, what is shader in queue? What is work graph? So, so one sentence to summarize, it is a brand new data flow module. So we add something in Spiral V, so that the application can say this shader can be represented as nodes, and there will be many nodes with a virtual queue for each one. So you can see these large light gray rectangles are virtual queues, and there will be payloads that flow between nodes and getting queued. Payloads are just medium for work distribution, and the node will launch when it is appropriate. There will be several factors. The first thing is, of course, it should have enough pending payloads, but also it only also depend on the GPU driver and the graph itself. And during the runtime, the driver will do some medical things, do some code merge, reordering, sorting to make sure the graph is optimal. But for the user, just build a graph from the logical angle. And the most important thing that the user or the application can control is the launch mode. So first thing, we have 3 categories. So the first thing is called broadcasting, where you basically have one payload comes in, then it get broadcast to fixed or dynamic size of grids of work groups. So what I mean by fixed here is that you can specify upfront when you build the graph, or you can put it into the payload. So if you put it into the graph, you make it static, then a driver can obviously do some optimization. And another mode is called coalescing, where you have multiple payloads over here, as you can see, and it get filled up to some degree in the virtual queue. And we just basically launch a single work group for up to those n payloads. And it's up to the application to decide like how many payloads can be in queued at most. And the third one is called thread mode, just kind of like a special case for coalescing, where you just launch one thread per payload. Each thread are independent and they're mining their own payload. And I guess some of you may have a question: what if my renderer is very complex and it has maybe like thousands of shaders, right? Then inside of the graph can explode and become prohibitive very easily. So our answer is nodes can actually be node arrays. So meaning that if we zoom in, the node can have a bunch of shaders with the same input and launch type. And how to switch node is fairly easy. You just the payloads are allocated and queued for a specific node ID. So according to the node ID, it will get routed to the targeting node, right? And in terms of topology, I think the most interesting feature is that we allow self-recursion. It basically means the node can enqueue payload for itself. So you can see these are bluish payloads here. They are launched, or sorry, enqueued by the node itself. So, and merge and branching are also allowed, meaning that the graph doesn't necessarily have to become the tree-like structure. It can be two nodes and can send the payload to a common one. So in this way, you can it can be very flexible to specify the dependency of GPUs. And another feature, I think the last one. Another feature is called mesh node, because I only talked about compute ones. So if the whole graph can only handle compute, it's not very functional, right? So there's one more type of node called mesh node, where they are just mesh shaders that can set payloads. They can only be the lead node, so meaning that the whole graph can be perceived as a huge task shader, and they get embedded into several mesh pipelines. So in this way, I think we have some functionality overlapping between the shader in Q1 and the device generated commands one. So because node replacement can also be perceived as shader switching, right? And in terms of memory consumption, obviously we don't need those worst case size allocation. And the reality is we offer you a range of buffer sizes, and if the application allocate the maximum size, then best performance guaranteed. However, if the minimum size is still can saturate the whole graph. And the mesh launch is a variant of forecasted mode, as you can see. So here's the summary of these two extensions. I've talked about memory, and in terms of performance, device generated command still requires some intervention from the host, because you will have barriers, and you have to tell the GPU where those indirect command buffers are in the GPU, right? So it still more or less requires some intervention. However, for world graph, once you design a graph, then it will become largely autonomous. And in terms of flexibility, device generated commands is linear. So for example, if you have a very complex dependency chain, you have to unroll, linearize everything, do some type of sorting. It can be very hard and almost impossible in some cases. However, for shading queue, for world graph, you can see this topological graph. As for expressiveness, I think both of them are very powerful. So as I said, it can device generated command allows you to customize command layout. However, in contrast, the shader in Q1 is a genuine producer-consumer network, which can achieve global representation. Here are some miscellaneous topics. So what to expect next? We will update our progress in AMGPU Open, so stay tuned. And we will release, because this spec has come out in a few weeks before, so we will support it. Our driver will support this extension early next year. And here are some links for both of these extensions. If you want to have a look, you can browse, open your browser and take a deeper look. And we also provide beta driver for Mesh Node, which is released in October this year. We also provide a sample app to showcase how to use this extension. And my thanks also goes to some of my colleagues, because without their helps, this speech is not going to happen. And in the long run, of course, we are looking forward a cross-vendor standardization of this extension. So if you have any input, like suggestions, you think some functionality is missing, you can send me an email. And there's still a lot of work to be done, because maybe you have a feeling that it turned out to be a huge black box, and you can only draw the graph design a graph and good luck. So there will be some validation, CTS, profilers, tooling, all kinds of stuff, right? So these are our to-do items. And side topic, Vulkan 1.4, our AMD software driver is about to support Vulkan 1.4 early next year, since it has been released in this forum. So this is information to those who are using AMD graphics card. And you can read a disclaimer, and that's it.
Thanks, Ken. Yeah, the word graph stuff is really cool. I look forward to seeing what people are going to be able to do with it. Right, and next up for the next two talks, Shannon Wood from NVIDIA, starting off by talking about Slang.
Hey, thank you very much. Hi, I am Shannon Woods. I work at NVIDIA, and I'm also the working group chair for the newly formed Slang working group at Kronos. There was a Birds of a Feather session dedicated to Slang yesterday, but today I would like to focus on what Slang means for Vulkan. So some folks in the room are probably familiar with Slang, but to give a very brief overview for anyone else, Slang is a shading language and a compiler that ingests that shading language and outputs a bunch of formats for use across a bunch of APIs and platforms. Slang's syntax is really similar to HLSL, but with a number of new modern language constructs added, which I'm going to talk about in a sec. Slang also provides helpful on-ramps into Slang from HLSL and GLSL. It's essentially able to compile most HLSL and GLSL syntax as is. And the latest development for Slang is that we're now part of Kronos. Slang began development more than a decade ago as a collaboration between NVIDIA and Carnegie Mellon. And this fall, NVIDIA donated the language and the compiler to Kronos so that it could be managed collaboratively. That doesn't mean that NVIDIA has pulled back any of its engineering support. In fact, we've increased the amount of engineers working on Slang even further. Now, Slang can compile to all of these targets, but this is the Vulkan Birds of a Feather. So the one that we're really interested in for this talk is Vulkan. So I'm going to zoom in there. Now, developers have quite a few options for high-level shading languages to use when targeting Vulkan. So you might have questions like, why are we adding another shading language? Well, we think that Slang is a great addition because it provides modular code management, automatic differentiation, deployability to diverse targets, including Vulkan, an open source compiler, and open governance. And we think it's awesome because it complements the other shading languages in the space. We're taking a different but complementary evolutionary path, and we think that developers benefit from having choices. A lot has changed since the legacy C++ days, and languages across the ecosystem, including C++, are learning from some of the choices that C++ made way back when, and pursuing more modern language structure. While Slang originally shared syntax with HLSL, the way that Slang and HLSL are pursuing modernity aren't exactly the same, and we think that's a good thing. HLSL is converging closer to modern C++ and leveraging tooling that's available in that ecosystem, while Slang is making language choices that are closer to those of Swift or Rust. We believe that a diversity of shading languages in the ecosystem encourages competition and innovation. If we take multiple approaches to solve a problem, we can provide developers with options and collectively converge on a set of solutions that are optimal. We also think that it is important for there to be language options which are actively evolving under the influence of multiple voices rather than a single corporate entity. GLSL once occupied that space in the ecosystem, but GLSL development has stymied in the era of explicit graphics APIs like Vulkan. I want to emphasize that Slang is by developers for developers. Slang's community management policies are intentionally built for technical work to happen completely in the open, using best practices from the open source community. Contribution is open to any interested developer, not just Khronos members, and not just for simple bug fixes, but truly having a voice in the language development. We've documented the processes for becoming a committer and a code or language owner on our website. We also do all of our technical debate and decision-making processes in the open on Discord, where anyone can observe or join. You can hop on right now and provide input to discussions where we're figuring out our priorities or get support for upstreaming your own custom target. Essentially, if there's a problem that you wish shading languages could solve, you can join us and work to get a solution landed in Slang. If you're wondering how Slang might fit into your existing Vulkan workflow, I have good news. Support for Slang already exists in much of the tooling that you're using today. For example, you can use step-through debugging of Slang in RenderDoc, thanks to both Slang and RenderDoc supporting non-semantic debug info. You can also do direct shader inspection in NVIDIA's Nsight tool to follow the shader as it goes from Slang to SPIR-V all the way down to shader assembly. And it's also easy to get Slang. As Spencer mentioned just a bit earlier, it's now distributed as part of the Vulkan SDK alongside GL Slang and DXC. Slang also provides extensions for support in Visual Studio and VS Code so that you can get syntax highlighting, auto-completion, and error annotation as you type. The language server module is provided as part of Slang, so you can also integrate it into other IDEs as well, as long as they support the language server protocol. So Slang can do all the things you're already doing with other shading languages. That's cool. But what does it do that other shading languages don't? Probably the single most exciting feature Slang offers is support for automatic differentiation. Now, differentiable functions are at the heart of gradient descent approaches to optimization, and that drives stuff like 3D scene reconstruction and differentiable path tracing. But before now, performance-critical, real-time differentiable code has had to be written by hand, which means you have to write and maintain 2 copies of all your critical shaders, the original shader and the differential form. And any changes that you make to one have to be made and maintained correctly in the other. This is a headache you might be willing to put up with if you're doing research, but it becomes a maintainability problem in production. But support for automatic differentiation is built into Slang. It's a first-class language feature. What this means is that you need only to annotate your function as differentiable, and then Slang can automatically generate both the forward and backward differential forms. And Slang is able to produce code that's equivalently performant to hand-tuned CUDA code. So you don't have to sacrifice maintainability for performance or vice versa. This is also pretty cool because it enables a shared ecosystem between machine learning code and existing rendering systems. The Slang code that you write for training is the same code that you use for rendering. Now, I talked about modern language design choices and how they power Slang. Perhaps those most central to the spirit of Slang are modules, generics, and interfaces. Modules provide separable compilation and visibility control, while generics and interfaces are a modern approach to parameterized polymorphism. Now, all of these language components enable code reuse and reduce the type checking and other work that the compiler must do on the front end, and that translates to reduced compile times. Now, Slang is within 10% of the GLSLC and DXC native compilation times if you give it the same monolithic shader code that you're used to using. But if you make use of Slang's modules, you can skip a significant portion of the time that you would otherwise spend on semantic checking. And in some of our internal benchmarks, this amounted to about 16% of overall compile time. Just taking a quick look closer at modules, generics, and interfaces, because they're commonplace outside of shading languages, but it's a new approach within the shading language world. As I mentioned, modules provide separable compilation, and the reason that this has compilation time benefits is that you compile a module once and then reuse it from multiple sites. And visibility enforcement makes sure that code is used safely and coherently across the code base. So if you're working on a large amount of code with a bunch of people you might not even necessarily be talking to every day, that's a big benefit. Slang also provides generics and interfaces, which allow type checking to be done on the generic type rather than only the type substituted version of the code. And that not only reduces the amount of redundant work that the compiler must do, but it also enables developer support tooling like IntelliSense to provide more useful feedback as you code, because it can make better deductions about how a generic type may be used. This is as opposed to the wait until you compile and then spew out lots of angle brackets that you might be familiar with things like templates. So if all of this sounds absolutely wonderful, but you're worried about the difficulty of switching to Slang, don't worry, it's not hard. Some big code bases have already made the move, including Valve's Source 2 engine, which replaced all of the other HLSL, or all of their HLSL with Slang, and that's now in use in production. They did this with minimal code changes, about 10 lines throughout their entire HLSL code base to switch to Slang. Autodesk is also putting Slang to the test in their Aurora path tracing renderer, both for Vulkan and D3D. The team working on that reported that ray tracing was trivial to get working on both platforms. And just an 8 megabyte binary gets you support for all of Slang's targets, not just Vulkan. Slang has no dependence on LLVM. When we are targeting CPU side formats, we generate C++. And the runtime performance, as I mentioned earlier, is able to meet or beat handwritten code, even when using advanced features like generics and dynamic dispatch. So we are a very open project, and we would absolutely love it if you joined us and got involved today. I showed a very similar slide to this yesterday, where I told everybody our Discord was at 180 members and counting. We're now at 200 and counting. So please hop on and join us. I know that the link isn't spelled out here. If you have trouble finding it on Google, just come grab me afterwards. I can spell it. You can also file an issue or a feature request on our GitHub. Start a discussion in our GitHub forums. Submit a pull request if you're ready to become a contributor, or if you want to go even farther than that, read up on how to become a committer. We would love to have you. And this delightfully asymptotic graph is a comparison of the GitHub stars on the GitHub code bases for all of your favorite shader compilers, and Slang there in red has caught up to its peers very quickly. So thank you. We're very excited about all of the engagement and excitement around Slang. Thank you. But don't clap yet. I have to give you another presentation. You may have seen me talk about Slang today and yesterday, but I'm also actually here in my capacity as a member of the Vulkan Safety Critical Working Group. So I'm going to switch gears and tell you a little bit about that. So with GPUs at the heart of modern machinery, it's very critical that all workloads are fault tolerant. And if you're wondering why, well, consider the last time you were running a game on a desktop and ran into a driver crash. Usually you have to restart your game. You might even have to restart the PC or game console that you're running the game on. But we can't afford faults like this that could happen if the GPU is in a car or a robot on an assembly line or other embedded applications like that. So we need a graphics API that's designed to run in embedded systems, in a car, in a robot, anywhere. And open API that hardware drivers can implement so that app developers can build their apps across a wide range of GPUs with fault tolerance in mind. So this is the soul of Vulkan Safety Critical, or Vulkan SC for short. I'm going to talk about a few things today. I'll cover how workloads get shared between AI and graphics on the GPU, why Vulkan SC is the preferred solution. I'll walk you through an example use case. Then I'll talk about how you would go about moving to Vulkan SC. I'm also going to discuss where the different perception to AI to visualization use cases are in the industry, and where you can get Vulkan SC today. So the most familiar example of a Vulkan SC use case I can provide for you is an autonomous vehicle or a car with driver assistance. So today, those vehicles need to perceive and visualize an incredible amount of data in real time. Autonomous vehicles can have up to 6 cameras and a LiDAR system and a radar system, all perceiving the surroundings. From your traditional backup camera and your surround view, where the cameras are stitched together to provide a top-down or 360-degree view of potential obstacles, to parking assistants that scan the vehicle surroundings to find available parking spaces, to confidence views, where everything that the AI perceives in terms of driving lanes, traffic lights, and your surrounding vehicles need to be visualized in real time at 60 frames per second. And as the AI in the vehicle grows in capability, so will the data requirements and the amount of rich information that we need to visualize. So there are a few ways today of ensuring that the AI compute workload can be safety certified, from isolating it in a VM and then doing the display in a separate VM, all the way to having separate multiple GPUs and having those GPUs communicate via a serializer. The flow is the same in both cases, where all of the data exists in one VM, the one that's doing the thinking. But since the display is not safety certified, it needs to be sent across to the other VM via some sort of inter-VM communication channel like IPC. This can be extremely inefficient due to the available bandwidth on the communication bus, which is small. So not all of the data that's available to the AI can be displayed. And if you think about the surround view, that requires streaming real-time high-definition sensor data from several cameras across VM boundaries and then deciding which side of that boundary that you stitch them together. With Vulkan SC, you can access the graphics directly inside the safety VM. And the reason for that is because Vulkan SC promotes fault tolerance. It does this in three main ways. First, it guarantees that concurrent workloads between AI compute and graphics can operate without interference. The latest modern GPU designs can even partition GPUs so that graphics and compute work can be done simultaneously, but in isolation. For example, NVIDIA's Hopper and later GPUs ship with this feature. Secondly, they eliminate GPU processing stalls due to dynamic allocations and shader compilation. Vulkan SC does all of its allocations during initialization, and then all the shader compilation must happen offline. You've definitely seen stalls on desktop apps when you hit a new area and a bunch of shaders load, or even worse, if you've seen this happen in embedded apps. It's very difficult to predict when the GPU will decide to allocate memory or when a shader compilation is going to start in GL or Vulkan. So in Vulkan SC, we remove these from the runtime. And then the final way is robust fault handling and reporting. The specification for Vulkan SC has clear guidelines on how faults must be handled. For example, in NVIDIA's Vulkan SC driver, we clearly signal what is a warning versus a fault and the criticality level thereof. In addition, we ensure that the logs are secure and that they don't leak any potentially sensitive information outside of the VM. So Vulkan SC is the driver that you want at the heart of the modern car or robot, or essentially anywhere you're doing work on a modern GPU. With NVIDIA's Vulkan SC implementation, it's unlikely that we will ever jank the screen or deschedule AI compute workloads within the same GPU. This is kind of magic if you consider how we try to do the same thing today in a self-driving car without Vulkan SC. But the status quo today is actually to do GLES for graphics in cars. Mainly because it's easy and there's a large availability of graphics talent out there from mobile apps that already knows GLES. For current vehicles, that might be the right choice. So you might reason, well, why don't I move to GLSC? But the world is accelerating with AI, and graphics should be moving to support AI in all industries. And if we compare the two safety critical graphics, we can see there's a clear winner. So GLSL is designed for safety, but it's not multi-threaded, and it hasn't moved since GLES 2.0, which means that it has no compute support. Shaders for GLSC are also from the GLES 2.0 era, so they're extremely limited in functionality compared to Vulkan SC. On the other hand, Vulkan SC is built on top of Vulkan, so it has zero copy by default. It is multi-threaded friendly, and it supports modern shading languages and features. For example, you can write your shaders in GLSL or HLSL or Slang, and they will be supported in Vulkan SC. And on top of that, Vulkan SC supports compute functionality, so it's kind of a no-brainer. So how do you get started writing apps for Vulkan SC? Well, one way to do it is start with Vulkan. After it works on Vulkan, all you have to do is shift your pipeline and shader compilations to be cached using the Pipeline Cache Compiler tool, PCC. Then move dynamic object and pool reservations to static reservation during initialization. It doesn't take much to add Vulkan SC. For a simple Vulkan triangle, it's about 50 lines of code. And then for Lime SC, which is NVIDIA's internal visualization SDK for autonomous vehicles, it takes about 1,000 lines to shift all of the dynamic object and command full reservations. If you want more details on this, you can get them on the Kronos website. So I talked about one use case, but there's a lot of places where Vulkan SC can help. On the NVIDIA Drive IX platform, we're shipping Vulkan SC for our surround view system. And then in robotic environments, Vulkan SC can help do things like reduce jank for stereo views in remote operation. And then Core AVI has been focusing on avionic graphics and compute acceleration with their VK Core SC product. So you can try Vulkan SC out for yourself today. For Core AVI, you'll want to visit their VK Core SC website for more information. On the NVIDIA side, you can download Vulkan SC for desktop and start developing on discrete GPUs. You'll need RTX 2000 series and up. It's also included in NVIDIA Jetson products and the Drive AGX products. Hammering this point home, you don't need an embedded device to start developing with Vulkan SC. If you have an NVIDIA desktop GPU card, RTX 2000 series or later, you can start today. Just follow that link for more information. And even better, you don't even need a GPU that has its own Vulkan SC driver. Any GPU that supports Vulkan can use the Vulkan SC emulation layer, which we're rolling out. Now, the emulation layer is not meant for production use, but it's good for development, prototyping, and evaluation. But you should ask your vendor for native Vulkan SC support so that you can deploy it to prod. There are a lot of tools and resources to get you started. Obviously the specification is where you'll want to look for all of the gritty details on exactly what's in it. But you can also check out their validation layers just for Vulkan SC. There's a collection of tools and the aforementioned emulation layer, all available at this set of links, which will be available in the slides once they're distributed. And if you have any questions, here are 3 wonderful places to get answers. There's, of course, the Kronos Vulkan SC landing page. And then you can check out the information from both Core AVI and NVIDIA, who are currently providing Vulkan SC drivers. And I believe that is it.
Yeah, so that's a really cool onboarding and bootstrapping story for Vulkan SC. And that brings us to the end of our talks. So first of all, we'd like to thank the speakers. And then straight on to Q&A, I guess. So are there any questions?
It's a small thing, but I noticed on this one of the first slide, the website domain was still khr.io, and like the IO domain, top level domain might not exist in the future. Is there any plans to address this?
So the khr.io thing is just like a short redirect thing. So Kronos.org is still the official website. I guess I'll have to talk to our webmaster about what we'll do about short links in the future. But yeah, for now it's only used for short, convenient links for presentations like this. So we should be okay, I think.
Thank you.
Well, I'm interested in the drawbacks of Vulkan SC. But if Vulkan SC is simply safer than vanilla Vulkan, then it might even be better to use Vulkan SC on the desktop application and so on. So what is, I say, drawback or overhead performance hits or any limitations with Vulkan SC compared to vanilla Vulkan?
So I would say probably, the biggest, most obvious drawback is that you can't do runtime shader compilation. So all of your shaders have to be compiled ahead of time. I think that the main purpose of Vulkan SC is really for places where you need to certify safety, that you're absolutely never ever going to run into a GPU crash. I am not equipped to answer questions about performance drawbacks. I'm not aware of any, but that doesn't mean they don't exist. So I'll have to refer you to the websites on that one. Oh, you're a dynamic memory allocation. Yeah, you have to allocate everything right up at the top. That's what I think, but I'm not prepared to stake my life on it, but I think so. Yeah.
I do have a question. So, as an application developer, one of the major things that is like concerning for us is the landscape of Vulkan support on Apple devices. Vulkan BK is kind of okay, but it's still stuck on Vulkan 1.2, whereas today we're Vulkan 1.0 now. What do you like? How do you see this going forward? Do you expect any major investment on Vulkan BK, or can we expect and kind of like improvements, especially given that Apple has released game porting toolkit? Do we have any high-level talks on like, hey, can we implement Vulkan on Apple platforms finally, please? Yeah, I think that's my question.
Neil, I think this might be one for you.
So MultiK is the existing solution, and it's being used in production by many developers, and they are happy. You're right. There's a understandable lag between the very latest in Vulkan and the layer catching up, but MultiK will continue to be evolved. But there are other options on the horizon that not decided yet, but the Mesa stack potentially is going to have some options to produce a portability layer in the same way, but leveraging all of the machinery that the Mesa stack has. So that may enable the portability layer to be more agile and be more developed. That's something that we're investigating, but again, there's no decisions yet. Of course, if you don't want to run Mac OS on the Apple hardware, there's always the Honeycrisp drivers that run native Vulkan on Apple hardware, and a shout out to Alyssa, who's done amazing work to make that happen. But at this point, we have no indication that Apple will enable any third-party APIs on their platform.
I have a question regarding Slang. So for PyTorch integration with CUDA, can Slang be used to replace that part? And also, is there any already existing samples on
Slang currently has a module called Slang Torch that I'm not super familiar with the Python side of things, but I believe that Slang Torch is you can basically use that to bind between Slang and PyTorch. Slang will also generate binding glue code between Python and Slang's CUDA kernels for you. I am unfortunately I'm from the real time side, so I don't have a lot of experience in that. But essentially, the answer is yes. For more details on how to do it, I can send you to our Discord where there are people who live and breathe it every day.
I have a question about GPU-driven rendering. So to my understanding, Vulkan was already even developed or designed to minimize the host program time and so on. How much performance gain do you get by using GPU-driven programming? Worst case, best case, and average scenarios?
Well, unfortunately, because there's basically we just launched this project recently and support dual cores. So right now we don't have performance numbers, and we will try to do some experiment and finally release it in our GPU Open regarding performance-wise, how does it perform? Because for one thing, we don't have really, we can have a sample app that use shading queue, but we don't have nothing else to compare with. If we write a naive code like simple jaw or something, of course the work rate can be faster, but right now we don't have concrete numbers of it.
Thank you.
I also have a question regarding the GPU children about and there's already many rendering algorithms. I'm curious about what algorithms can benefit from GPU rendering, because so far I only noticed maybe nanite, maybe some culling. Do you think there will be a revolution using the GPU driven in the future?
Sorry, I don't really understand. So you want to ask like, what can GPU culling benefit the application?
I mean, do you think there will be a revolution using a fully GPU-driven pipeline in the future?
Of course, as AMD, we firmly believe that GPU-driven rendering is a future, because I have already stated a lot of downsides of unnecessary intervention from the CPU. That's what we believe the future is.
And besides culling, besides nanite, you aware of any other algorithm that can benefit from GPU driven?
So far, I don't know.
Thank you.
I mean, one case that does is anytime that you want to dynamically create geometry, so like procedural geometry use cases is one. You mentioned culling is another big one. Yeah, I think particularly the procedural cases and kind of dynamic LOD type cases are potentially really interesting. Right, Lacey?
I actually have a question regarding the HDR attachment format. So in XR application where there is probably a final composition happening after you render the you have your Vulkan rendered. Seems like if you're using RGB pen A2, we are like reducing the precision on the alpha channel. I wonder if that is going to have an implication there.
I got the last sentence.
So if we're using RGB pen A2 as the format, we're sacrificing the alpha precision.
I think I can answer the question. So regarding RGB 10 alpha 2, so the alpha 2 bits of the alpha channel is a problem. So I believe in the future there might be some formats, like I believe Apple support that it's RGB 10 and alpha 8. So that could be used as a future format. And that's one case. And another option is you can just use floating point 16-bit. So that can solve the alpha channel problem, because we also noticed that if you are using 2 bits of alpha channel, you will get some false contouring when you do alpha blending. So there will be some solution, and the existing solution is the floating point 16 bits.
Thank you.
Right, just one thing. I think that there was a question before about the GPU-driven rendering, and there was a paper today presented also on high throughput rendering for embodied AI, where they do something similar like in CUDA, and they procedurally generate a lot of training data. So I think that might be a good example also where they don't want to like sort of configure all those render pipelines again and again from the CPU. They just want to do it like once, and then from the GPU like create a task graph. So I imagine like in these probably gonna offer like something like that, but which might not be the case. Just to answer the other question, I don't know if that's easy.
Yeah, okay, great, thank you. Okay, there's no further questions. I guess all of the speakers will be here for a few minutes. If anyone wants to come talk to us one-on-one, we'll be here. We'll be happy to hear from you. And yeah, thank you for coming to our BOF.